Cosmology seems to be heading for a showdown on one of its most basic questions: how fast is the universe expanding? For more than a decade, two types of measurement have been in disagreement. Observations of the current universe typically find the rate of expansion, called the Hubble constant, to be about 9% faster than do predictions based on early universe data. Researchers hoped that the James Webb Space Telescope, the most advanced telescope in history, launched in late 2021, would help to settle the question once and for all. But consensus has so far failed to materialize. Instead, a Nobel Prize-winning physicist from Johns Hopkins University says that new data collected by James Webb, which confirms previous findings about cosmic expansion, may mean scientists have misunderstood the universe. So, is cosmology really in crisis? And do we need an alternative to the theory of the expanding universe? All this and more will be discussed in today's episode. There were two significant pieces of observational evidence that came in at about the same time, in the early part of the 20th century. First, astronomer Vesto Slipher had been observing a variety of nebulae in the sky, leveraging a novel technique at the time known as spectroscopy. By breaking up the light from these objects into their various wavelengths, Slipher noted that many of them had the same spectral lines we were familiar with from the known elements, but were systematically shifted, like something had stretched them to longer wavelengths. One possible explanation was that of a Doppler shift, as though these objects were moving away from us. Second, starting in 1923, Edwin Hubble, with his assistant, Milton Humason, began, quite by accident, identifying individual stars in these spiral and elliptical nebulae. Originally seeking to observe novae, Hubble realized that some of these flares were actually periodic, brightening and faintening variable stars. By knowing the nature of these objects and observing how bright they appeared, the distance to them could be determined. Lo and behold, when you combine these two pieces of information, a new picture emerged, one where, on average, the farther away a galaxy was from us, the greater its light appeared to be shifted toward the redder, longer wavelength part of the spectrum. If this discovery had been made before Einstein's general relativity had come along, perhaps we would have resorted to a number of alternative explanations for why this was occurring. Perhaps there was some sort of lossy medium in space as light traveled through it, causing the light to lose energy as it propagated through the universe. Perhaps there was some sort of intergalactic matter present, extincting the light, particularly at shorter wavelengths. Perhaps these galaxies were all closer together in the past, and the ones that moved faster relative to each other now wound up farther away as higher speeds, over time, lead to greater distances. But that wasn't the order of events, at least, as far as our understanding of physics was concerned. We had already confirmed the predictions of general relativity in spectacular fashion during the total solar eclipse of 1919, and had already realized that space and time were not absolute quantities in our universe, but were woven together into the fabric of space-time. Putting all of these things together meant that, once we realized that the universe was filled with matter and other forms of energy all throughout it, we couldn't have a static and stable universe. The universe, instead, must be either expanding or contracting. The observations pretty clearly indicated that it was expansion, not contraction, that was occurring. As is often the case in physics, when the equations reveal that there are multiple possible solutions, you have to look to the actual universe itself to pick out which solution corresponds to your physical reality. Although, in theory, the universe could have been either expanding or contracting, expansion is what it turns out it's actually doing. But the expansion rate of the universe can be a confusing concept that is perhaps best introduced by analogy. Suppose you have a rubber band that is 2 units long with a mark at the center. You attach one end of the band to an unmovable hook and hold up the other end to ensure that it is straight. Thus, The end you are holding is 2 units away from the hook, while the mark is 1 unit away. Then, imagine that you grab the loose end and stretch it so as to double the length, taking 1 second to do it. The end is now 4 units away from the hook, while the mark at the center is 2 units away. Thus, the mark moved 1 unit in 1 second, while the loose end moved 2 units in a second. The key point is that the spot more distant from the hook moved more quickly than the one nearer the hook. In the language of cosmology, the velocity of a spot on the rubber band is 1 unit per second for every unit of distance from the hook. The expansion of the cosmos is exactly the same. More distant objects in the universe are moving away from the Earth quicker than closer ones. In round numbers, distant galaxies move away from the Earth at a rate of 70 kilometers per second for every million parsecs of distance. A parsec is a historical unit of astronomical distance equal to 3.26 light-years. Thus, a galaxy at 1 megaparsec from the Earth moves away at a rate of 70 kilometers per second. A galaxy 2 megaparsecs away moves at a rate of 140 kilometers per second. This rate is called the Hubble constant, and the basic idea is very well established. However, there are several ways to determine the Hubble constant. The first and most straightforward way is to measure the distances to galaxies and simultaneously measure their velocity. You can then determine the galaxy's velocities as a function of distance. When you do this, you find that the Hubble constant has a value of about 73 kilometers per second per megaparsec, with an uncertainty of merely 2.4%. Different groups obtain slightly different values, but they are all quite consistent. This value of the Hubble constant is called the late-time version, as it is determined from the period relatively late in the lifetime of the universe. There is another way to determine the Hubble constant by examining the conditions of the cosmos shortly after it began. The universe began 13.8 billion years ago in a cosmic cataclysm called the Big Bang. While it is somewhat misleading, one can imagine the Big Bang as a vast explosion, which included a glowing fireball and a rumbling sound. In the very early universe, the fireball was impenetrable, but when the cosmos was a mere 0.03% its current age, the expansion cooled the universe enough that light could escape the fireball and travel across the cosmos. While the universe was glowing hot at that early time, the expansion of space over the eons has cooled it until the light is no longer visible. Indeed, that once visible light is now only microwaves, which can be detected by radio antennas. This primordial whispering remnant of the Big Bang is called the cosmic microwave background, and it was first detected back in 1964. The sound waves of the Big Bang were locked into the early fireball, resulting in tiny variations in the cosmic microwave background. Astronomers can measure those variations very precisely. Using those patterns, they can take all factors known to have any relevance to the Big Bang and subsequent evolution of the universe, and predict a value of the Hubble constant for our current day. This approach hinges crucially on the measurements of these variations in the cosmic microwave background, as well as various theoretical ideas. Using this early time information, astrophysicists predict that the Hubble constant should be about 67.5 plus or minus 0.5 kilometers per second per megaparsec. That's the problem. That's the puzzle. We have 2 fundamentally different ways of how the universe has expanded over its history. Each is entirely self-consistent, but the early time and late time measurements simply disagree, and this specifically is what is referred to as the Hubble tension. This phrase describes the fact that, even though scientists are aware the cosmos is constantly ballooning outward in every direction, as we can clearly see stars and galaxies drifting farther and farther away from us over time, they can't perfectly pin down the rate at which that ballooning is happening. That leaves us with a pretty major chasm in our understanding of the universe. Potentially, this discrepancy either suggests our instruments are not intelligent enough, or maybe we're awfully wrong about that theoretical prediction. In other words, perhaps the models that presently thread our understanding of the universe are missing something. In 2019, a number of high-profile physicists even famously gathered at the Kavli Institute for Theoretical Physics in California to officially try and resolve things. That ended with a headache. As particle physicist David Gross, a former director of the Kavli Institute for Theoretical Physics, put it, "We wouldn't call it a tension or a problem, but rather a crisis." And ever since, scientists have continued to diligently work out where they might have gone wrong, crossing off possible explanations for Hubble tension on a list you can check out here. Which brings us to today, when scientists expect James Webb, a more refined telescope with the latest technologies available, could solve one of cosmology's deepest mysteries. First off, having said that the contributions of this observatory are immense, with it, we can see the universe through new lenses. The level of detail we receive now is outstanding. We are able to see the past of our universe, observe and discover exoplanets. The most distant galaxies ever discovered were thanks to this advanced telescope. And that's why scientists hope that this telescope will help us refine the Hubble constant once more and better understand the rate of expansion of our universe. However, what the Spaceborne Observatory obtained was contrary to scientists' expectations. In a nutshell, it showed that the so-called crisis is probably not due to technical issues, with measurements made by its telescope sibling that boasts a very relevant name, the Hubble Space Telescope. And this is a big deal, because Hubble observations are one of the most common features that scientists use to decode the Hubble constant, or more specifically, Hubble observations of Cepheid stars are. As lead study author Adam Rees, professor of physics and astronomy at Johns Hopkins University, who shared of the 2011 Nobel Prize in Physics for his co-discovery of dark energy, said, "With measurement errors negated, what remains is the real and exciting possibility we have misunderstood the universe." Initially, some scientists thought that the disparity could be a result of a measurement error caused by the blending of Cepheids with other stars in Hubble's aperture. But in 2023, the researchers used the more accurate James Webb to confirm that, for the first few rungs of the cosmic ladder, their Hubble measurements were right. Nevertheless, the possibility of crowding further back in the universe's past remained. To resolve this issue, Rees and his colleagues built on their previous measurements, observing 1,000 more Cepheid stars in 5 host galaxies as remote as 130 million light-years from Earth. After comparing their data to Hubble's, the astronomers confirmed their past measurements of the Hubble constant. In the words of Rees, "We've now spanned the whole range of what Hubble observed, and we can rule out a measurement error as the cause of the Hubble tension with very high confidence. Combining Webb and Hubble gives us the best of both worlds. We find that the Hubble measurements remain reliable as we climb farther along the cosmic distance ladder." In other words, the tension at the heart of cosmology is here to stay. As such, now some strongly believe that the best way to solve the problem is to look for new physics that may explain the discrepancy. Some astronomers believe that Earth resides near the center of a supervoid, a large region of less than average density, roughly 2 billion light-years in diameter. The presence of this supervoid would affect our measurements of the expansion rate, because galaxies within the supervoid generally flow outward toward the void's edges. So, when we go to measure how quickly the universe is expanding by looking at nearby supernovae, they get an extra speed boost because of this outward flow, which could possibly explain the tension. A team of researchers followed this line of thinking in a paper recently accepted for publication in the monthly notices of the Royal Astronomical Society. But the existence of the supervoid itself may stretch the bounds of what our standard cosmological models can provide. It might just be too big. So to explain the existence of the supervoid, researchers have turned to monde, short for modified Newtonian dynamics. This is an alternative hypothesis of gravity originally proposed to explain the behavior of galaxies without needing dark matter. But monde itself doesn't do a good job of explaining the properties of the largest structures in the universe, and so the researchers had to add another ingredient. a new kind of particle known as a sterile neutrino. Essentially, sterile neutrinos are a different kind of dark matter that can work with MOND to explain large structures in the universe, like the local supervoid, which is ironic considering that the whole point of MOND was to get rid of the need for dark matter. So by leaning on a giant supervoid in our local region of the universe, a new theory of gravity and a new species of dark matter could enable researchers to resolve the Hubble tension and explain a relatively new result. This could show that galaxies in the local universe appear to be flowing away from us faster than they should in standard cosmological models. It's an unproven but intriguing combination of thoughts, and we will likely have to add something to our understanding of the universe to eventually explain the Hubble tension. But it's easy to add complexity to a model in order to achieve a desired result, and have that complexity add more headaches. In this case, the goal is solving the Hubble tension, and this model does so, at least in a preliminary fashion. But it takes an awful lot of complexity to get there. Not all astronomers agree that the local supervoid exists. It's tough to assess the overall density of the universe at these kinds of scales. Not all astronomers agree that the existence of the supervoid breaks our standard understanding of cosmology. It may be perfectly reasonable without leaning on new physics. Not all astronomers agree that the presence of a supervoid would distort our measurements of the Hubble constant. Supernovae may be largely unaffected, and few astronomers believe that MOND is a viable theory. In fact, the vast majority of astronomers and cosmologists don't believe that MOND works at all, especially considering that it still requires introducing some form of dark matter to explain the variety of observed structures in the universe. The sterile neutrino idea required to make this model work is purely hypothetical. An intriguing idea for sure, but not yet on solid ground. And lastly, for this model to work, the Milky Way would have to sit near the center of the local supervoid, not out near the edges, which is a difficult coincidence to include in any viable cosmological idea. This research could lead somewhere fruitful and possibly generate an interesting idea that could resolve the Hubble tension. Currently, the conclusions are based on relatively simple models of the growth of structures in the universe, and the next step will be to implement this idea in a more faithful simulation. And ultimately, the evidence will decide the issue. Next, let's shift back the attention to James Webb. Recent reports of James Webb detecting signs of life of a distant planet outside the solar system are, unfortunately, somewhat premature. That's the conclusion of research conducted by scientists from the University of California, Riverside, or UCR for short. While likely to disappoint all of us eager for the confirmation of extraterrestrial life, however, it doesn't mean the telescope won't find traces of life in the atmosphere of an extrasolar planet or exoplanet in the future. The recent excitement around the potential detection of life signs on an exoplanet started in 2023 when the Webb telescope detected potential biosignature elements in the atmosphere of the exoplanet K2-18b, a super-Earth located around 120 light-years from Earth. Though many exoplanets are extreme, violent, or at least alien in nature, whether they're blasted by intense radiation from their stars, lack a solid surface, or are frozen relics at the edge of their systems, K2-18b was a tantalizing target in the search for life because it is rather similar to our planet. K2-18b is between 2 and 3 times the width of Earth, with 8.6 times the mass of our planet. It's also located in the habitable zone of its star, the region neither too hot nor too cold to support liquid water. The exoplanet is thus theorized to be an ocean, or Hycean world, replete with liquid water, a vital ingredient for life as we know it. Unlike Earth, however, the atmosphere of this exoplanet seems to be mainly hydrogen rather than nitrogen. As team member and UCR project scientist Shangmin Tsai said in a statement, "This planet gets almost the same amount of solar radiation as Earth, and if atmosphere is removed as a factor, K2-18b has a temperature close to Earth's, which is also an ideal situation in which to find life. The key takeaway from the 2023 investigation of K2-18b, conducted by University of Cambridge scientists using the James Webb Space Telescope, was the discovery of carbon dioxide and methane. These molecules were detected without traces of ammonia, which indicated that this should indeed be a Hycean world, with a vast ocean under a hydrogen-rich atmosphere. But there was also the hint of something else, something very exciting. In the words of Tsai, what was icing on the cake, in terms of the search for life, is that last year these researchers reported a tentative detection of dimethyl sulfide, or DMS, in the atmosphere of that planet, which is produced by ocean phytoplankton on Earth. That means if DMS is accumulating to detectable levels, there must be something on K2-18b, possibly a life form, producing it at 20 times the rate found on Earth. However, because the detection of DMS was inconclusive, even the team leader of the investigation, University of Cambridge scientist Niku Madhusudan, urged caution with regard to the discovery of DMS. He said future James Webb observations would be needed to confirm its presence in the atmosphere of K2-18b. But not everyone got the memo. However, that inconclusive nature of the DMS detection also prompted the UCR team to follow up on the detection. What this second team found with computer models accounting for hydrogen-based atmospheres and for the physics and chemistry of DMS was the original data was unlikely to point to the detection of DMS. The signal strongly overlaps with methane, and we think that picking out DMS from methane is beyond this instrument's capability, Tsai said. That means the telescope will need to look at the world with instruments other than the NIRISS and NIRSPEC used to conduct the initial investigation that detected hints of DMS. Fortunately, Madhusudan's team is continuing to observe K2-18b with James Webb's other primary instrument, the MIRI, as the researchers gather more intel about the environmental conditions on the exoplanet. As team leader and UCR astrobiologist Eddie Schwieterman said, the best biosignatures on an exoplanet may differ significantly from those we find most abundant on Earth today. On a planet with a hydrogen-rich atmosphere, we may be more likely to find DMS made by life instead of oxygen made by plants and bacteria, as on Earth. Is this slight disappointment a setback for scientists searching the cosmos for signs of life? Not a chance. Nor does it overshadow the initial investigation's importance as a step forward in our understanding of Hycean worlds, some of the most promising targets in that search. As Tsai asked rhetorically, why do we keep exploring the cosmos for signs of life? Imagine you're camping in Joshua Tree at night and you hear something. Your instinct is to shine a light to see what's out there. That's what we're doing too, in a way. In addition, as a piece of good news, the Webb telescope is set to begin investigating the spectacular light shows of solar system giants Uranus and Saturn. Two separate teams of astronomers at the University of Leicester will use the $10 billion space telescope to study auroras over the gas giant Saturn and the frigid ice giant Uranus. The aim will be to explain in greater detail the processes that create these polar light shows over different planets. As Henrik Mellin from the University of Leicester School of Physics and Astronomy, who will lead the Uranus investigation, said in a statement, the James Webb Space Telescope is already changing how we perceive the universe, from the solar system, our very own cosmic backyard, to the first galaxies formed at the beginning of time. I am thrilled to have been awarded time on this remarkable observatory, and this data will fundamentally shape our understanding of both Saturn and Uranus. Auroras are familiar to skywatchers over Earth as the stunning northern lights and southern lights, which can be seen along the poles of our planet when they appear. These light shows are generated over Earth when charged particles that stream from the sun's solar wind strike our planet's protective magnetic field, known as the magnetosphere. These particles travel down magnetic field lines and stream out behind Earth. But as they do this, they interact with particles in our atmosphere, creating glowing light. When the sun blasts out high volumes of stellar plasma in so-called coronal mass ejections, auroras are more prominent and can be seen at lower latitudes over Earth. Though auroras have been seen over other solar system planets before, and they should be possible around any planet with an atmosphere and magnetic field, less is known about these alien light shows. Currently, relatively little is known about the auroras of Uranus, an ice giant with an atmosphere of water, ammonia, and methane. It was actually only last year, after 3 decades of investigation, that a research team from the University of Leicester School of Physics and Astronomy, led by PhD student Emma Thomas, confirmed an infrared aurora around Uranus. Because of a past impact with a roughly Earth-sized body, Uranus is tilted at a 97.77-degree angle. This means that its poles are orientated almost directly toward and away from the Sun, and its auroras are positioned around what would normally be the equator for a solar system planet. As Mellon and his colleagues use the telescope to observe the auroras of Uranus, which is the 7th planet from the Sun, they will investigate something suggested by this previous discovery of Uranian auroras. Are the auroras of this distant planet responsible for keeping it warmer than expected? Webb's study of Uranus will begin early in 2025. It will capture images of the ice giant over a single day for the planet, which lasts around 17 Earth hours. This should allow the team to map auroral emissions across a whole rotation of Uranus's magnetic field. The scientists will also aim to discover if emissions are produced when the Uranian magnetic field interacts with the solar wind, as happens over the Earth, or if interacting charged particles come from sources within the system, similar to how Jupiter creates its auroras. There is also the possibility that Uranus's auroras are created as a combination of these phenomena, just as Saturn's auroras seem to be generated. The James Webb's Saturn Aurora Project, led by Boston University Center for Space Physics scientist Luke Moore, will observe the gas giant's northern auroral region for an entire 10.6-hour Saturnian day. This will allow the team to monitor how the temperature of this region changes as the gas giant rotates. By revealing Saturn's atmospheric auroral energies for the first time, the team hopes to learn more about the sources of charged particles within the gas giant's atmosphere that drive its auroras. Both Webb's giant planet studies will be conducted using the powerful Space Telescope's highly sensitive NIR-CAM instrument. Once these findings are in hand, scientists can better understand the processes that create auroras in the solar system and the role these mechanisms have on Earth in particular. Perhaps the results can help astronomers glean information about auroras around planet beyond the system too. Extrasolar planets or exoplanets, which are targets for the search for life outside the solar system. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.